Alright, hey class, this is our second to last lecture. Kind of excited. Alright, we're going to talk about oxidation and reduction. We briefly talked about it, and you've actually seen these two figures earlier on in the semester. Essentially, oxidation results in an increase in the number of CZ bonds, where Z is normally O, but it can be the other things that we're used to. So just kind of keep that in mind. Oxidation, we're going to increase that number of bond, and reduction, you're going to decrease that number of bond. Kind of the way I like to think about reduction, though, which I think will be more helpful for today, is that it's going to be an increase in the number of CH bonds. So oxidation increases oxygen, reduction increases hydrogen. So that might be kind of an easier way to think about it. You can see that kind of illustrated here as we take something that has only hydrogen and we add oxygen to it, we say it's being oxidized, it's undergoing oxidation. And if we go opposite, if we have something that has a whole bunch of oxygen and we add more hydrogen to the carbon, so here we have two hydrogens on a carbon, 3 hydrogen on a carbon, 4 hydrogen on a carbon, we say that's been reduced. So that's undergoing reduction. We are going to stick with just reduction today. So reduction is the main name of today's game. We'll talk about 3 different types of reduction reactions. So no matter which reduction occurs, we are going to have to add H2 somehow. So we'll always be adding H2, not just one hydrogen, it will generally be H2. And the way to do that is through the following. Oh, also, by the way, today we're mainly working on alkynes. So we're going to be adding hydrogen to alkynes. Okay. The first way we can do that is using molecular H2. So you'd react some kind of alkyne with molecular H2, and you'd add a catalyst, usually palladium, platinum, or nickel as a specific catalyst, and usually you're indicating that it's a catalyst by writing PDC, C meaning the catalyst. And PD, for example, this is probably the most common one you're going to run across. This is a really strong catalyst, and we'll talk about how it works. Then for reduction, we'll talk about adding a reduction with another set of situations is when you're going to have sodium and NH3. So this is kind of weird if unless you really sit and think about it for a while, that H2 really is 2 H pluses with 2 extra electrons. So if we put 2 H pluses and 2 electrons together, you'd get H2, right? So the way that it adds to an alkyne in this situation is that the sodium itself will be the thing that's giving off 2 electrons. Sodium ionizes really well. It likes to give off electrons. And then NH3, which we already know is cool with giving off a hydrogen, right? So if you have 2 of them and 2 of them, you'll have 2 electrons, 2 H pluses, and therefore you have an equivalent fraction of H2, which you can use for reduction. Last but not least, you could add hydride and a proton. So, so an example would be, these would be all situations of hydrides. If you remember, boron really only wants to have 3 bonds. It's happy having 3, and that's why it will actually not just give off hydrogen, it'll give off a hydrogen plus its electrons. Remember, a hydride is that. So it will give off this whole set of stuff right here, and so will aluminum if it's got 4 hydrogens on it. So we call this borohydride, and we call this aluminum hydride, and you can compare it with any cation metal that you want. Then you would want to follow it up, because that would these things give off the hydride, and then you would want to follow up with a proton that comes from water or an alcohol. All right. So again, metal hydride reagents act as a source of H- because they contain polar bonds. So again, they want to hold on to what they've already got, and it's fine to give off that negative charge. Okay, so let's just go ahead and get started kind of talking about all these things, because until we do them, it's just going to be kind of frustrating. So in the reduction of alkenes, and eventually we'll move on to alkynes here. In alkenes, you take a pi bond like this, something with that is an alkene. You add H2 with a metal catalyst, and you can get an alkane, full alkane out of it. So for example, in this first one, where we had a double bond here, you just add H2 and PDC, and you get this. Again, this catalyst could be nickel or platinum, but the main point is you added H2 and a metal catalyst, and you went from an alkene to an alkane. Okay. It adds in syn addition, meaning they'll both be on the same side, right? But at the end of the day, well, I guess it will matter because you've got the methyl group here and here. So in this case, it is pretty important, but a lot of situations it won't change anything because it's just hydrogen. All right, so these are two good examples that you should just memorize and understand. H2, PDC, adds in syn addition. You can take an alkene and you can turn it into an alkane. We know all sorts of ways to take an alkane and turn it into alkene, especially if it's an alkyl halide. Okay. Hydrogenation, we talked about that term a little while ago when we were talking about hydrogenated oils, for example. So hydrogenation is the term that essentially means adding hydrogen. Okay, so in the last example, we said you took an alkene, you added H2 and PDC, and you got the alkane. And that is true. Energetics end up being a little bit important in terms of what you're going to get and which catalyst you should use. And we're going to kind of explore how that's different now, and then why we would change catalyst here in a little bit. So for example, if you have something that's cis, we already know that the cis conformation is less stable. It's adding, these are electron inducing carbons here and here, and they're making the whole molecule a little bit less stable in terms of how the electrons are distributed across it. But here we have more even distribution because you have some here, and it's equal and opposite effect, so you have a nice stable trans alkene. Okay, so if you react either of those with H2 and metal catalyst, you're going to get the same exact product. The only difference is it took less energy to do this one because this happened to be more stable already. It was already a lower energy structure. So when you went through and you added your H2, less energy is released, and we would say that the heat of hydrogenation was lower. Decrease heat of hydrogenation. Okay. All right, so keeping that in mind, trans things will have a lower heat of hydrogenation. We can go through and look at this, and maybe, I think the first one comes rather intuitively. Here we have cis, here we have trans. We know that the trans is going to have the lower heat of hydrogen. Oops, the lower, I saw larger. Lower. This has the lower. I don't know what I'm saying. This has a larger. Just like up here. If you have cis, it's less stable, so it takes more energy to occur. I promise. I've got it. I just got lower and larger confused in my mind, apparently. All right, but let's look at this next one. This maybe isn't as intuitive, but I hope at this point that we can look at this thing and we can say, this one right here is more stable. Why is it more stable? Because these electrons are being shared here and here, and we want that double bond to be closer and more substituted here. So here we have a tri-substituted carbon, and over here, or tri-substituted double bond, and over here we only have the di-substituted. So if you remember, when you're looking at either end of the double bond, this thing has 1, 2, 3 things on it, and this one over here only has 1, 2. So this is tri-substituted double bond, and this is a di-substituted. This tri-substituted is definitely going to be more stable, and because of that, it will have the lower heat of hydrogenation. That would have the larger heat of hydrogenation. So the more stable thing will always be lower in energy and take less heat for hydrogenation. Okay, now it says which has a smaller heat of hydrogenation. Oh, they're really killing me here. So in this case, we have a terminal alkyne, and we have the internal alkyne. The terminal alkyne is going to be less stable. The internal is going to be more stable. The same rules apply. If it's more stable, it takes less heat of hydrogenation, and therefore that would be your answer, because it's asking for smaller in this case. All right. So now we go to increasing the rate of hydrogenation. Again, it has to do with stability. Obviously, if it requires more heat, then it's going to be a longer rate. It's going to take longer. So you can increase the rate of the reaction by making it essentially more stable. So, or increase the rate by making it less stable. It's going to be more likely to react. So if it's unstable, it's going to want to react really, really well. If it's more stable, so this is more stable, it's more substituted. This is less stable. The less stable thing is obviously going to be more reactive because it's not happy where it is. Over here, we're more stable, we're totally happy, so we don't need to react as quickly. Okay, given that syn addition occurs from both sides of a trigonal planar, these would be trigonal planar. We have 1, 2, 3 things. These are sp2 hybridized, therefore they're trigonal planar. Something you want to remember from the something that you're going to really want to remember for your final exam is trigonal planar stuff, tetrahedral stuff, etc. It says draw all the isomers formed when each compound is treated with H2. Okay, well, if syn addition is occurring and you're adding H, you are going to the either end of the double bond. So for example, in this first one, when we go to add H2, okay, we add H to either end of this double bond. So this one gets an H and this one gets an H, right? So this H right here could add as a wedge, in which case this one would be a wedge, or it can add as a dash, in which case this one would be a dash. Now the only thing that ends up mattering is this methyl group right here, because this methyl group right here is going to become a stereogenic center. So if the hydrogen comes in as a wedge, what you're going to get is going to force that methyl group to be a dash. And if it comes in as a dash, you're going to force that methyl group to be a wedge. Okay? So you'll get both of these. Let's look over here. The exact same thing. The hydrogen can come in here. The hydrogen can come from the back. And that's going to force this whole thing, this methyl group right here. Don't forget, when I say methyl group, it's weird to think about, but there's the methyl group right there. Right? There was one right here. And that's what we were talking about on what was on the wedge or the dash. So the hydrogen can come in here, or the hydrogen can go in there. The other hydrogen is going, oh, this is a CH2, by the way. The hydrogen can come in here, making this a CH3. And that's how, that's why when you're going to add it, it can add via up or down on the cyclohexane. So we might have the methyl group do that, or we might have the diastereomer over here, where the methyl group adds to a wedge like that, or a dash like that. Okay. Here we have a brief sneak peek of OChem 2. Although right now we're pretty much talking about alkenes and alkynes and adding hydrogen to them, you can imagine that we also reduce things that have oxygen on them. In that previous chart we had, we said that when we reduce something with oxygen, it can go from something like this, like a carboxylic acid, to this ketone, to an alcohol, and then eventually no alcohol at all. And that's what you can do. You take this aldehyde, this double bond carbon to oxygen, and you can reduce it and make it an alcohol, or you can take a ketone and reduce it and also make it an alcohol using the same exact parameters. Again, it says this is OChem 2. I think it's chapter 17, and we won't be getting into it, but it is good to know. I actually think it's kind of simple. It'd be kind of fun to get into OChem 2 a little bit there. Okay, now we talk about reduction of alkynes. There's all kinds of reductions in alkynes. Okay, there are 3 main reactions here, and I don't really like how I laid this out, so I'm going to add a lot of notes here. Okay, if you take an alkyne and you react it with a very specific H2 parameter, so I'm not even going to do this, we're going to react it with 2H2 and PDC. So a very specific catalyst that we're going to use. The reason we're going to use PDC is really strong. So it can take a triple bond and it will go all the way to an alkane. And we'll learn pretty soon that we won't even stop. We'll just go straight from the triple all the way to the alkane, and it's pretty much impossible to isolate the alkene. Okay, if we want an alkyne and we want to create a cis alkene, it's also a very specific set of parameters. It's H2, one equivalent, but it's also what we'll have to use the Lindlar catalyst. And we'll talk about what Lindlar catalyst is. It's actually a set of different different compounds that react cohesively together to make a good catalyst, but not so good that it takes it to the alkane. So notice it goes to alkene, specifically a cis alkene. If you have an alkyne and you want to take it to a trans alkene, the best way to do that is not use H2 specifically. Remember, we said sodium, which gives off an electron, and NH3, which give off a proton, is going to be the best situation to form this thing right here. And it would just be one equivalent in each of these. Why just one equivalent? Because we're not forming the alkane, we're forming alkenes. This is for trans, this is for cis, and you will have to know them, okay? And if you want to take it all the way to an alkane, you do this. Now really, that's probably all you need to know for the rest of the chapter, but let's get into each of these 3 reactions in a little more detail. Okay. So it says, let's focus on making a cis alkene from an alkyne. All right, so when you used PDC, you will get a cis alkene, but again, this PDC is such a strong catalyst, it's going to continue going, and you're going to get the alkane, and you won't be able to isolate the alkene. So if you need an alkene as like an intermediate to do another reaction, you couldn't use this. You have to use something different, something a little lighter. And so if you use something a little lighter, like the Lindlar catalyst, which is again is this set of different compounds, this set of different compounds, when you can just write Lindlar catalyst instead of memorizing all those individual compounds. When you react an alkyne with that, H2 and Lindlar catalyst, that's when you can isolate your cis compound. All right, we won't do a mechanism for this because it occurs on the surface of a metal, and it's just very weird. I did kind of skip over how this works as well, but again, it is more of just a surface kind of situation. So let me take a little detour and show you briefly how any metal catalyst works. So you have a surface and it's covered with a whole bunch of atoms of the metal. So let's say we've got like palladium, okay? And then you add to that palladium 2 hydrogen atoms. Those are your 2 little hydrogen atoms. And then in comes, let's say, your alkene. It does something called adsorb. It's absorption, not absorption. And it's going to adsorb these hydrogens onto the carbons under these conditions. So essentially then you'll get, and there's a series of different equilibrium reactions that you can do, but none of them are what we're used to. There's no arrow pushing. It'll pull up those hydrogens and suck them onto it, and then it is free to go, and you have the alkane. That's about as good as I'm going to do it. And then you have the beautiful alkane left, and you have your initial palladium catalyst. That's what makes it a catalyst. It started off as a catalyst and ended as a catalyst. Excuse me. Okay, so when we're talking about all these things occurring on palladium or on a metal catalyst, we're generally talking about this absorption issue, where there is no arrow pushing mechanism like we're used to. Same thing goes for the Lindlar catalyst, where we're still talking about palladium. Okay, now it says let's focus on making trans. So we know how to make a cis alkane. We can use that Lindlar catalyst, right? We know how to make a full alkane. We can use the PDC. Now we want to make a trans alkene. To make a trans alkene, you're just going to add the sodium and the ammonia. Okay. So if you take this but2-ine, for example, and you add it, you're going to make it a trans alkene. The mechanism here is one that we haven't seen before, because we haven't worked with individual electrons yet. Individual electrons are one single dot of that lone pair of electrons that we're used to seeing. If you have just one single dot, it's called a radical, because it's totally crazy. No. All right, we talked about sodium ionizing very easily. This is what it means when we say sodium ionizes. It gives off an electron. So if you have some sodium and it gives off an electron, that electron can then adhere to this carbon right here, which forces this bond, because carbon can't take more than 4 bonds, it forces this bond to hop up on here and become a lone pair of electrons. But now this electron right here is still a radical. Now, though, this, what we call a carbanion, a carbon with negative, so it's right here, carbanion is carbon with a lone pair on it, that's negatively charged, can then grab a hydrogen, and just like that, now we've formed a carbon-hydrogen bond. And it just kind of repeats the same process again. Once again, now you have that radical that's hanging out there. The electron comes and joins it, making it a carbanion, and then it can grab hydrogen, that can go back to there, and we now have a newly hydrogenated triple bond. Now, notice it's always going to form trans. The reason it will always form trans is because this electron attacked from one direction, forcing these electrons up here. It will never be like one electron trans hits here, causing that. It's always going to be attacking from one side, forcing the electrons up to the other side. So it will give you generally the trans. If it does come this way, it's not going to be a primary at all, and that's exactly what this is saying. So you might get cis or trans, but no matter what, the trans would be the primary one that is going to be produced. All right. Okay. Yeah, I know it talks about like this is the vinyl. That makes a lot of sense. This is the vinyl carbocation, which is a lot more stable than over here where we have this cis situation. Okay, so here's what we just learned, and we really could have just jumped right here from the very beginning, because I think it's a lot of information and a lot of stuff saying, hey, there's a reaction here, but we can't really do it. There's a reaction, and we're not even sure how to do it. And in fact, that's what, if you read the first paragraph of this chapter, it pretty much just says there are so many different ways that we could be getting these products, and it's really hard sometimes to isolate all the intermediate steps. So we're just doing our best to guess on how these reactions occur. Okay, so again, here's a summary. If you have this and you take H2 and PDC, two equivalents, you'll get the alkane. If you react it with the H2 and a Lindlar catalyst, you'll get the cis alkene. And if you react it with sodium and NH3, you'll get the trans alkene. Okay, it says what product was formed when this long thing is treated with each reagent. I better grab some extra water, or extra paper here. Okay. So, first let's draw this thing. Looks pretty fun. You got a methyl group. Does some kind of ether to a CH2, to another CH2, to a carbon which is triple bonded to another carbon, to another CH2, and then I've got what looks like two methyl groups on that carbon. So I got 1, 2, 3, 4, 5, 6, 7, 8 carbons in total. 1, 2, 3, 4, 5, 6, 7, 8. I'm missing one. Oh yeah, I see it. I see it. Okay, let's redraw this. Sorry guys, I would normally cut this, but I'm not gonna. Okay, I think I got it now. I was missing it right there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Okay, so now we have this beautiful thing, and we are going to go ahead and react it with a variety of things. The first one is excess H2 and PDC. We know that when you add excess H2 and PDC, this is a super strong catalyst. It's going to take it all the way to an alkane, add a whole bunch. And then again, this was excess. It's going to take it all the way down, and you're going to get the alkane. So we'll have something like that. 1, 2, 3, 4, 5, 6, 7, 8. Cool. Okay, so this was A. And B, if we take the same thing, I don't think I want to draw it again. Do you guys? Probably not. And you take one equivalent of H2, and the Lindlar, Lindlar. So cis. I don't know. However you're going to think about it. Maybe Lindlar would be a great name for your sister. However you're going to remember it. It will form a cis alkene. So here we've got the same thing. And then we'll go. Right there is going to be the double bond. 1, 2, 3, 1, 2, 3. We got a double bond, and we know that this excess stuff right here has to be cis. So it means I'm going to form it down like this, over, and then like that, if that makes sense. So this is the only way I could think of to draw it easily, is just kind of repeat the same thing. And then when we get to the double bond, determine where it's going to go. All right, so this was B. Now we have C. In C, it said excess Lindlar catalyst. Oh, great. So H2 and Lindlar catalyst are, Lindlar in general is a very weak catalyst compared to PDC. So PDC will take it all the way to an alkane. It doesn't matter if you have excess or no excess, you're going to get the exact same product. So I'll save us all time and do that. Okay. So with or without, if you have one equivalent or excess, is just going to come and form this no matter what. That's as strong as it can take it, from an alkyne to an alkene. And that's the whole reason you use Lindlar, is because you want to make an alkene. Okay. Last but not least, for D, it asks us to add Na and NH3. Now this is just one equivalent. If it wanted more, it would have had 2 and 2, but it didn't. And so we're going to get A very similar situation as we had here, so let's start off drawing it exactly like that. So there we're at the double bond, but again, this will form the trans alkene. So now we'll have it go up and over, like that. So this one was cis, and this one is trans. All right, so hopefully that makes some sense. Okay. Again, this could form the cis, but it would be not the primary, because it's not stable, the intermediates. All right, last but not least, we have the reduction of the sigma bonds. Okay, we said reduction, if you remember, could be adding carbon-hydrogen bonds, or another way that we talked about it is that you could also reduce CX bonds. So let's go ahead and look at how that would occur. Again, here we have an aluminum tetrahydride. We know that aluminum tetrahydride, aluminum wants 3 bonds, and therefore it's cool giving off one of these hydrides. And that's exactly what's going to happen. It's going to end up giving off hydride, and that hydride is going to attack here, and this is going to leave. Very much an SN2 type mechanism. And we'll talk about, in fact, you can see it right here. So here, the aluminum, the hydrogen with the bond, keep in mind the arrows leaving from the bond. These are the electrons that are going to attach to this carbon. So very different from the past where we're taking things from here and grabbing a hydrogen. Here we're taking the whole bond and going over there. And then this X leaves. So again, this is very SN2. And because of that, primary alcohols are far more, primary alkyl halides, excuse me, are far more easily reduced than secondary or tertiary. And that's because it's SN2. Because it's SN2-like. Okay. And then we have this other one where you can have some kind of epoxide, and the same thing happens. You're going to attack, but the less substituted carbon. So hopefully that makes sense. The hydrogen is going to go on the less substituted carbon, forcing these things up, and then you could follow it up with some water, because again, you'll have just the oxide here, and you're going to want to protonate it with water or something similar. All right, last but not least, this is draw the products of each reaction. So let's see if we can put to use what we just learned. We should see this thing and immediately think of this as a reducing. A reducing agent, because it is. And all you're going to do is just a single substitution. This is primary, so it's highly likely that that this alcohol will be easily reduced. And instead of chlorine, you can just leave it like this. Or if you really, really want to like emphasize that you add an extra hydrogen, you can put a hydrogen there. Maybe like box them in and be like, hey, look, we just substituted for that. Okay, and then we can do the same thing for this. Remember that the hydrogen, the hydride, which will be like this, AlH3, and you can have some lithium kind of chilling over here, that this whole set of electrons is going to want to attack the less substituted carbon in an epoxide. Then when we follow it up with water, we're adding an H to this oxygen. And you're going to end up with a methyl group, because it's going to force this to go up. It's going to become oxygen. So you still have the methyl group right here, and you'll now have an alcohol right there. And then here and here will be your new 2 hydrogen, or new 1 hydrogen. And you could just leave it off, and this would not be stereogenic, so you could leave it as is. So yeah, hopefully that helps and makes some sense. I think it's pretty cool stuff, a little different than what we're used to, but hopefully not too overwhelming. There's mainly just those 3 reactions that we learned at the last, plus this one. So really 5 reactions in total, and I think you guys can do that. When we come back for the rest of chapter 12, we will talk about oxidation. See y'all, have a good day.